At a commercial port, long-term theoretical planning physically manifests as tons of heavy steel swinging onto transport vehicles. Once a shipping container is in the air, the underlying logistical decision is locked. But the data driving that physical movement is inherently unstable. Consumer demand forecasts constantly shift, often revising themselves days or weeks after purchasing, staffing, and supplier contracts have already been executed. We can map these decisions across a production timeline, tracking the sequence of required logistical steps from the present moment into the distant future. This timeline displays a standard production schedule. The initial periods, labeled T1 and T2, represent immediate actions. Because these steps are already underway, altering them would cause massive operational disruption. This irreversible block of early decisions is known as the setup prefix. Notice the fluctuating demand curve above the later uncommitted periods. Planners need to know a precise mathematical limit. How far can future demand deviate before a new production path becomes cheaper, forcing the company to abandon this locked setup prefix? A recent candidate release from Evidence Press addresses this problem. It proposes an exact rational computational framework designed to calculate a guaranteed safe radius, a quantifiable margin of error for these forecast variations. Supply chain resilience does not require perfect clairvoyance. It requires calculating the exact mathematical boundary where your current, irreversible commitments break down. To locate that boundary, we first have to quantify the financial cost of producing and holding inventory between any two given periods in the timeline. The foundational logic relies on the classical Wagner-Whitin dynamic lot sizing model, which translates physical operations into predictable mathematical functions. This equation calculates the total cost for a single production arc. The first term represents fixed setup costs, a static block for initiating a run. The second half measures holding and production costs. As cumulative demand fluctuates, this expense scales proportionally. Because the variable costs rise proportionally while the setup costs stay flat, the resulting total path costs are mathematically affine in demand. This linear scaling allows planners to accurately project how the cost of any specific sequence of decisions will behave, regardless of how erratically the demand forecast shifts in the future. We can expand this single arc calculation to evaluate full multi-period production paths extending across the entire planning horizon. A planner compares a nominal path, their current active schedule, against a competing path, an alternative schedule if future demand shifts. This graph charts both options against changing demand to locate where the alternative schedule overtakes the original. The precise point where these lines intersect is the path tie. By measuring the horizontal distance from the origin to this intersection, we get the exact margin. This distance defines the absolute maximum margin of forecast error permitted before operational logic dictates switching entirely to the competing path. Finding this breaking point against one isolated competitor is a simple algebraic calculation. However, real supply chains present an immense set of potential alternative paths, demanding a more robust computational framework to guarantee the setup prefix remains the correct initial move. The planner's primary responsibility is protecting the immediate commitments. If future, uncommitted choices change, the prefix remains intact. A true disruption only occurs when an outside path becomes cheaper than every single possible continuation of the locked setup decisions. The computational challenge lies in mapping out all of those potential continuations to locate the ultimate breaking point where the prefix fails entirely. The paper structures thus into a prefix deviation directed acyclic graph. This maps locked nodes branching into divergent, uncommitted futures. Calculating the failure point across all branches yields the strong radius. Discovering this exact mathematical limit is computationally demanding. Instead of waiting for a mathematical proof of exact complexity, the framework utilizes a Charnes-Cooper formulation and an inverse linear program to calculate a frozen comparator lower certificate. Using a 3-period example from the paper, we map two bounding boxes. The inner box, the frozen certificate, is a mathematically guaranteed lower bound, assuring the prefix is safe. The outer box is the strong radius, marking the true failure limit, but remains computationally intensive. In live operational planning, an easily calculable, mathematically guaranteed safe zone holds far more utility than an absolute limit that cannot be quickly verified. The theoretical math must be executed by the software to produce this certificate. The public implementation runs entirely in exact rational arithmetic. This completely eliminates the rounding errors that standard floating point calculations naturally introduce. This terminal output demonstrates the exact computation. It emits rational witnesses, allowing operators to run independent producer-side checks and confirm the output against a specific SHA-256 hash string. Despite passing internal automated checks, this release remains strictly an unrefereed candidate. The underlying decision rule has not been validated in a working supply chain. The included dataset reconstruction relies entirely on stylized costs, rather than live operational data. Furthermore, the historical priority of the method is incomplete. A definitive assessment of novelty requires auditing a specific 1989 paper by Richter and Voris, a full text that was unavailable during the initial bounded review. Moving this framework from candidate status to accepted math requires independent reproduction, proof-assistant formalization, and ultimately prospective studies using genuine forecast vintages and actual cost structures. Progress in operations research requires drawing a strict boundary. We must explicitly separate a mathematically certified reproducible hypothesis from an operationally proven field reality.